So, without further ado, it is my honor now to turn over the podium to our Chancellor, Dr. Randy Woodson, for the official introduction. Chancellor.
Thanks, Ken. Good evening, everyone. So this is a real honor for me. You know, when you think about this university and you think about the people that have started their careers and have been impacted by NC State, there's no one that's a better example than Dr. Jim Goodnight. Dr. Goodnight is a PhD student here and then subsequently as a faculty member, got busy working in analytics associated with agriculture and spun out this little company called SAS. You know, there are people in the world that have the ability to see the future. And Jim Goodnight is one of those. Because I'm serious, if you think about the world of 1976 or 1986 or even later, people weren't talking about analytics. But Dr. Goodnight and his colleagues understood that the time was going to come when we were going to be buried in data and we were going to have to make critical management decisions and critical decisions across the world based on understanding data. And he's built an amazing company right here in Cary that does just that. And when you think about the impact Dr. Goodnight has had here at NC State, how many of you have had classes in SAS Hall? Okay, a fair number of you. I suspect a number of you might even be Goodnight scholars. Dr. Goodnight and his wife Ann support 200 STEM students at NC State with now full ride scholarships, full tuition, full room and board, and that's amazing generosity. Also, when you think about a commitment to education, the Goodnights represent that across the spectrum. There's no one more passionate and probably no one more outspoken about education than Dr. Goodnight. He and Ann have started a school in Cary. In fact, he'll leave here tonight to go to a dinner in celebration of that school, the Cary Academy. He's been very generous to NC State and always focused on helping this state get better. So it's my honor and privilege tonight to be with you and to introduce Dr. Jim Goodnight and his colleague, the CIO of SAS, Keith Collins, who also is a graduate of this great university. And Keith is going to have the challenge of sort of trying to manage his boss through a Fireside Chat. And I'm going to leave because I'm going to honor another one of our great faculty member, Jay Narian, from Material Science and Engineering, that's getting the North Carolina Award tonight from the governor. So I'm heading out there, and I actually think Dr. Goodnight is pleased with that because he loves to talk about the university in ways and not feel encumbered by the chancellor as he does that. So, Dr. Goodnight, Keith.
Thank you, Randy. Okay.
So Jim, I thought we might start by talking a little bit about this agriculture piece. Was there something that you feel like you were doing unique and approaching the problem right then at that time?
Well, our goal was to not have to rewrite programs over and over and over again to analyze all this ag data. So we began to realize that if we consolidated into a single program the ability to read data in and then move it out to disk, that from that point on we could read it back in and run it through any number of procedures. So really it was more a self-preservation than anything else. So that's one of the reasons. We worked in a group called the Experiment Station. There is one at every land-grant university, and the purpose of the experiment stations is to help design experiments for agricultural research, and then to analyze the data. Well, it turns out there's an experiment station at every land-grant university, and the Southeast, all the universities in the Southeast had an association that they would get together. It was called the University Statisticians of the Southern Experiment Stations, or USIS, or we used to call it useless. So that was the nickname of the organization, and they met once a year and pretty much talked about different things and partied a lot. We actually introduced SAS to this group in 1969, and they all liked it, and they all wanted us to sort of become their development staff. There was no reason for every experiment station to write programs, so they said they're just going to rely on NC State's work, and so that's how we began to get our first group of users.
So in fact, they recruited you back, and you were working at NASA for a little bit?
Well, I got about halfway through my master's program, and I had been working since the end of my sophomore year. That's when I took my first computer course on an IBM 1620. Wonderful. It was a wonderful machine. It was a base 10 machine. You could actually read it. You know, you didn't have to translate base 8 and all that kind of base 16 in your head. So, and it was a fixed length instruction set. The first two digits of each instruction was the opcode, followed by 2 addresses. And boy, it was just a very, very simple concept. But it was a pleasure programming. Of course, we used to program in machine language or assembly language, so you really got to understand what's going on inside the computer. And you know, I worry sometimes about computer science today with all the higher level languages they teach, that they don't get appreciation for what's actually going on inside the machine. Now, that wasn't your question, was it? What was it?
We were talking about the stint you did spend some time at NASA. You came back and
right. Yeah, I had I started working that summer after my sophomore year, after I took my first course. And there was only one course and was taught by the stat department. This was before computer science, so I predate computer science. But I had worked, 20 hours a week all fall and spring, and 30 or 40 hours in the summer. And I was just tired of working and going to school, so I decided to go out and get a job and leave my master's program, and I did. I ended up down in Florida working on the Apollo program for about a year. My wife's dad was terminally ill, and she was spending more time back here. So I said, why don't we just move back to North Carolina? So I called back up and said, can I get my job back? They said, sure, come back. And I did, and I walked in. There was my office. I opened the filing cabinet and pulled out the program I had been working on, sat down, and went back to work. So,
yeah. So around that time was when the IBM 360 came out. Was there something that you felt was unique that sort of launched the work you were able to do, talking about not having to rewrite the programs over and over?
Well, the 360 was a revolution in that it was a promise by IBM that you would not outgrow their architecture. They would always have another machine, another machine, another machine with the same architecture. Up until that time, every new machine that came out had a totally different architecture, and all of your programs had to be rewritten for that next level. So it was more of a marketing promise from IBM that things were going to be the same for a long time.
So for agriculture, you're dealing with taking in all the different data. You provided a framework for managing that data to drive it through the different analytics. What was the progression to sort of the next couple of industries, and what were the type of problems that people were really early on trying to attack with analytics? Well,
one of the very similar things to agricultural research, where you've got planned experiments where they're laid out very carefully. The pharmaceutical companies also have exactly the same thing when they do clinical trials. They establish which patients are going to get a placebo or another type of treatment, which ones are going to get the new treatment. And the experiments are designed. So the same analysis applied to the pharmaceutical industry as well. So most of the pharmaceutical industry started using SAS as well. And one of the reasons for that is in 1972, the university lost its NIH funding. Up until 72, NIH had provided most of the funds for the computers on all the college campuses. And when Nixon came in, he said, I only want to spend NIH money on research hospitals that have hospitals and that are medical research. So we lost our funding here, and we came up with the idea of going to all of our experiment station users and asking them to fund us. So they all pitched in and gave us $5,000 a year to continue the program. But they said, listen, we also want you to begin licensing SAS to some other organizations so that we don't have to foot the bill forever. So we said we would. And so that's when we went on what is called soft money at the university. That means you are welcome to work here, but you've got to pay your own salary. And that's what soft money is. A lot of professors are on soft money, but they're dependent upon the grants that they've got to fund them and their research. So that went on until 1976.
Now, do I remember correctly, can we quote ourselves as being one of the first open source companies? Because when you acquired the rights from the university to start SAS, wasn't there originally a set of open source that was available to anybody that wanted it, as you guys took it and then evolved it?
Well, we always shipped the source code with our compiled code so that people could study it to see exactly how we were computing things. We did that up until about 1985, when a small company out in Tennessee decided to use that and use our source code to write SAS for a VAX computer, which is a mini computer. Mini computers have sort of gone the way of horses, I guess, or whatever. They're gone. But that was the next phase of computing after mainframes. It was mini computers. Mini computers are about the size of a garage. Excuse me, about the size of a refrigerator. Lots of wiring inside, and they were great to be much less expensive than the mainframe, and a lot of departments were buying them to do departmental computing. Anyway, after that lawsuit, which we won, they were found guilty of copyright infringement. We were able to, we stopped shipping source code.
So that was an interesting time. You started off with assembler, mostly assembler, some Fortran. PL1 was coming along at the same time that the minis and the VAXes and everything were happening. But you somehow were early in on C and using C to rewrite SAS. Can you talk a little bit about what that discovery process was like and the decision to invest in C to rewrite SAS?
Well, PL1 and C are very, very similar languages. I think the main thing that PL1 had was global scoping of variables, so you could use them anywhere and within routines, and it would still know about them. But the problem was there really wasn't really good support for PL1 on anything other than the mainframe. There was some on the mini computers, but then the PCs came out about that time, and we had to figure out, well, how are we going to support PCs? Our users want us to support PCs. And let me tell you, that was tough, shoehorning a 32-bit system into a 16-bit processor. It was extremely difficult to get SAS to run, and we had to do all sort of overlays and everything else to try to get it to squeeze down to that size. But we finally did, but we decided the best way to do this, since C was sort of the prevalent language for PCs at the time, and C was available for minis. It was only mainframes that C wasn't available for. So we said, well, we'll just buy a C compiler company and go ahead and rewrite everything in C. So that's what we did. And we were suppliers to Microsoft, the Lattice compiler. And what we did with it, though, was to we were all basically doing most of our development at that time on Unix boxes, or what was that? What Apollo was their operating? It was similar to Unix. It wasn't quite Unix. So that's long gone as well. But we decided, well, why bother compiling on the mainframe? We'll just compile it on our Unix boxes that we're using and cross compile it. And cross-compile it for the PC, cross-compile it for the mainframe. So we had a very good compiler staff at the time, everything we did was cross-compiled to other machines so that we didn't even have to move the source code off its environment. So.
Yeah, I mean, one of the interesting side effects there was in the process of buying the Lattice C compiler, creating a mainframe C, which didn't exist at the time.
That's true.
Turned into a very good line of business for quite some time.
It did, yes. We then turned around and licensed it so that other companies could develop for the mainframe in C.
So that was an interesting set of events rewriting to the PC, going to C, and along came this idea of trying to create a framework that could run across all these different operating systems, delivering the software at the same time, what eventually became the multi-vendor architecture. Could you talk a little bit about how that evolution happened, the types of thought processes that went into generalizing the layer and getting that work done?
Well, we had, of course, developed SAS for the mainframe. We had another group that actually helped convert it to run under VMCMS. That was a virtual machine CMS. Essentially, you use the mainframe as if it were a personal computer. You were the only one on that machine as far as you knew. And we had a group that worked to convert it to run that way. And then we had another group that converted it to run on mini computers. And so now you've got a huge code base, a different code base for different machines. And when you're a software company, having different code bases is a boat anchor. You can't move. You got to, every time you turn around, you've got to go do the same thing you did for this code base. You got to go over and do it for that code base. So we knew that to be successful, we needed to have a single code base. And the code at that time was probably 2 to 3 million lines of code. And we didn't want to have to rewrite that for different machines. So we came up with the concept that, look, let's just write on top of each operating system, let's write a very thin layer, maybe no more than 4 or 5% of the entire system. And then once that layer is in place, we'll drop the 95% of the rest of our software down on top of it. Very similar to what they're doing today with virtual machines, with that layer in between. So that was our multi-vendor architecture. It worked extremely well. We're able to take advantage of all different hardware, but yet maintain about a 95% code base that was the same across all machines.
So what's interesting to me is what you just described is sort of like the POSIX layer that came around 10 years later. And so there's several examples where SAS has been well ahead of the market in terms of leveraging technology, moving technology. What would you say about how you've built SAS, about the talent you've been able to attract and retain, and why that's been successful? What is it about? What's the motivator that keeps really talented people at SAS? Is there something you think you can put your finger on?
Oh, hell, I think they just love to work for me, Keith. I mean, you know. But honestly, it's a challenge, you know, at SAS. We don't let anybody sit back and rest on their laurels. It's always, what are we doing next? We've got to stay ahead of the competition. So it's a constant battle of challenging our people in R&D to work a little bit faster, try to get things out quicker, keep ahead of the competition. Take advantage of all the latest new gadgetry that's out there, things like iPads. When that came along, we were blindsided because we weren't working on any kind of mobile stuff, because up until that time, the screens were only that big, and who cares about putting analytics on a screen that size? But bam, the iPad comes along, we've got real estate. We need to run on that. So had to have a group to take off and start running on that. But in reality, I think in IT and computer science, I've seen surveys that said that the challenge of the job is more important than the salary. Salary is important, but it's maybe second to the challenge. Yeah. And we've tried to develop a very innovative, creative atmosphere. And it's sort of the culture at SAS to be creative and to be innovative.
Yeah. Well, I know as a developer, when I would go to our users group conference, it was extremely rewarding. But also I thought one of the things that surprised me was the way customers would use our software in ways we never dreamed, and use it for much larger problems than we might have imagined. What would you say in terms of the importance of scalability and performance to the success of our product suites?
Well, that's where we are today, facing the challenge of big data. And that is an industry buzzword that it'll fade in another year or two because it's been around for a couple of years. You see, every 3 years there's a new industry buzzword. You know, it used to be cloud computing. That was it. We had to talk about that. Before that, it was software as a service. Now it's big data. And I think the next one next big term is going to be Internet of Things. That's already starting to appear. So we'll have all sort of venture capitalists pouring money into Internet of Things companies that are going to figure out what to do with it, just like they've done with the big data and poured money into that. Well, we started on this big data. We've always dealt with very, very large amounts of data, but it's not only big data, it's big computational problems as well. 5 years ago, it's been, 5.5 years ago, I was in Singapore at one of our conferences, and a banker comes up to me and says, you know, they've just installed our risk computational engine and it's working fine, but it's taking 18 hours. And I said, well, he said, we really need to understand our risk profile before the markets open the next day, and this is not going to get it, 18 hours. So can you speed it up? Well, I went back and I talked to our risk development staff, and after about 2 weeks, I finally understood what they were doing. If you're a risk developer, you don't talk much. It's, you know, just a sentence. You know, one sentence is about all you can get out of them at a time. So it took me a while, but I finally was able to understand the computations that they were doing. And lo and behold, it's going to take about 2 trillion operations to do that stuff. And on a processor that's only running 2 million instructions a second, it's going to take about 18 hours. I mean, we might have shaved 10% off with a little improvement here, a little improvement there, but it's still going to take 16 to 18 hours to do the job. So it's very clear that a single processor is not going to do the job. We're going to have to, for analytics, go to massively parallel or symmetric multiprocessing. Actually, what we've ended up with massively parallel symmetric multiprocessing. So, because the great thing about symmetric multiprocessing is you get to use all the memory. Everybody in that machine gets to use the same memory. And I mean, you got to be careful not to step on each other's toes. But if you're reading data in that everybody needs to access, you don't have to read it in one time. And then every processor on that machine can read that data and do what they're supposed to do with it. The problem was that our algorithms are all this single processor algorithms. You know, humans tend to think sequentially, especially in computer science, you know. Well, the first thing I need to do this, and then I need to do this, and that's how we have always broken down problems in computing. You know, solving each individual piece until you're absolutely positive that that's correct, then you move to the next piece and you solve that and so on. How do you do this in parallel? Our minds really don't think that way in parallel. Well, it was one of the first things that it dawned to me on is that we have got to build this really large matrix in memory. And we've always done it one row after the other, or sometimes one column after the other, either way. But it dawned on me, you know, it doesn't make any difference where these rows are. They don't have to be all together just because it's a matrix. Why don't we let this computer do the first 5 rows, this one do the next 5 rows, this one do the next 5 rows, so we can build this matrix in parallel and do it very, very rapidly. And that's how we got started in our concept of thinking about how do we move our algorithms into parallel modes. And today, that 18-hour problem runs in 12 minutes because we're able to spread it out, we're able to take advantage. And you know, the chip technology today, Intel is making denser and denser chips. Actually, the chips don't get any smaller. They stay the same size. They have for the last couple of generations. I brought one with me. Intel gives me these because they like you when I talk about their chips. But this is an Ivy Bridge chip. Sandy Bridge was a generation before, it was exactly the same size. But the Sandy Bridge had 8 cores. A core is the CPU, memory units, floating point units, graphical, everything that makes a computer except memory and disk. So essentially there were 8 computers on this chip during the Sandy Bridge era. That was and it was a 33 nanometer chip. Same size chip today is a 22 nanometer in the circuitry inside, and this chip has 15 cores in it. I think it really has 16, but they hadn't quite got their manufacturing down perfect yet. So it's either 15, but they're shipping 15 right now. And it's amazing if you think about it. The normal server comes with 2 chips. So now you'll have 30 computers inside each server that can address all the memory inside that machine. So you've got to think of ways to do things in parallel that takes advantage of the shared memory so that you're able to do things a lot faster. You're able to do computing a lot faster. You're able to handle much bigger data by bringing data into memory and scattering it across dozens and dozens of servers. You know, we can hold 10, 12 terabytes of data in memory. Now, if you buy a server with 2 of these chips on it, you can put a terabyte of memory on it and hang a few disks off of it for about $12,000. Then you run a Red Hat operating system on it, and you've got one heck of a computer, incredible computational powers for extremely small amounts of money. Now, one of my favorites, Dell makes it's called an R920. It's got 4 of these chips in it, in the single server. And on that one, you can put up to 3 terabytes of memory. So that is just an incredible machine. And we've got a number of those at SAS. And as a matter of fact, we've got a couple now that we can actually wheel around on dollies and take with us. So they're enough compute power to be almost the equivalent of a data center, and we can just throw it on the back of a truck and take it somewhere with us and roll it out. It's got its own wireless network, so we don't have to hook it up to anything. It's ready to go when we get there. So today's computers, the price and performance just gets better and better and better. These chips, each one of the cores operates at 3 billion instructions a second. And I said, well, how many cycles does it take to do a floating point operation? Because those used to take 8 or 9 cycles. They've got it down to 1 cycle. 3 billion floating point instructions a second. It's just absolutely amazing the amount of circuitry it's going to take to do that. But yet Intel has done it, and the next generation after this one is where they will improve it. So they have it's called tick-tock. Tick shrinks it from the last generation, and tock makes it improve. And then the next tick, they shrink it again. So we're at 22 nanometers now. The next generation after this will be down to 15 nanometers. And I'm not positive, I think about 5 nanometers is about the absolute limit, because that's the wavelength of ultraviolet light that they use to etch the chip with. So, you know, after about 5 nanometers, you start getting into the X-ray area, and that's just not going to etch anything. It's just going to go right through it. So, anyway, we're having great fun as a software company, taking advantage of these incredible computers that have these incredible chips. And our customers are moving off of a lot of the, you know, the more expensive, much more expensive computers, and moving to what we call this stuff commodity hardware. Because you can buy it, Intel designs it, they make the chips. A number of companies manufacture it. Dell does a good job, HP does a good job, Cisco makes it. Lenovo has now bought IBM's x86 business, so you know they're going to be into the business of x86 servers. So there's a lot of competition out there, and these servers are just going to get cheaper and cheaper and faster with more and more cores and much larger amounts of memory. And we've got to start thinking about handling all this tremendous power, a tremendous amount of memory. You know, you talk about the 360 days. Our first machine had 128K on it.
Yeah. So and so you hear the passion in his voice, and it is absolutely real. What was the ballpark cost for that first computer with
The first computer that SAS bought was about $2 million.
Right. So
And it was a used one. So.
yeah.
But it had 128K.
So,
And it was core. It was core memory. You know, today I still find myself calling it core. Back in those days, it was cores. It was these little donut holes. And you could open the cabinet and see 100,000 little donuts in there with wire going in each direction. And it was a ferromagnetic donut that got magnetized back and forth. And that's how we had internal memory.
yeah. But you can see, how motivated he's driving us about leveraging the technology at hand, because we can solve such different problems, the size and scale.
Problems that we never even thought about. You know, in the banking industry example, they need to compute the probability of default for mortgages. This is part of the government's requirement that they understand how much value they have at risk, part of their CCAR work that they do. But the problem is, one of the big banks we work with, they have 9 million mortgages outstanding on home loans. And to do logistic regression, and logistic regression takes in a whole bunch of variables and then tries to predict a number between 0 and 1. So it gives you a probability that this loan is going to default in a given period of time. Well, that is a nonlinear model, and nonlinear models don't have a solution. You have to guess at something and then do an iteration through the data and then improve your guess and do it again, go through the data again, improve your guess, go through the data again, do this 25, 30, 40 times. You've got to read that data that many times to be able to finally come to a set of parameters that have converged. Well, back in the old days, we had to read the data in every single time, every single pass. We had to read the data maybe 40 different times to do these iterations. And it took a lot of time. So there's no way you can handle 9 million. So they would subsample maybe 50,000 of these and then build the models on just 50,000 of these loans. Even that would take 4 or 5 hours. And then once they've developed the model, then they would go back and apply it to the entire data set. Well, now we say, don't bother sampling. Just do it on all 9 million, and we'll do it in about a minute and a half. So it makes the job of modelers and data analysts a lot easier, because they can fire up job after job and test many different models and iterate and try different methods until they're really happy that they have found the very best model that they can possibly find. It used to be they would have to give up after 5 or 6 tries because it was just taking forever to do it. But now they can do all that. They can do 100 iterations on this in a day's time to try to find the right model that best fits the data. So there's an example of doing jobs or problems that you never even would consider before that you now can do with the massive parallel computing. So.
So I'd like to back you up just a little bit, Jim, and talk about, because I want to make sure that the audience understands the importance of the core of the X prime X calculation, because that's key to so many of the things that we calculate. And together with that, with the simulations on the risk piece. Because you took a number and you put it out there on the number of computations, but I think the story of what that ties together, you're doing the X prime X and then doing the simulations, it really helps people see what the set of computations are going on.
Well, about everything we do in statistical computations is called they're row operations. When you multiply a matrix on the left times a matrix on the right, you're doing row operations. If you stop and think about it, The first row, you take the first row of the matrix on the left, and you lay it down sideways beside the matrix on the right, and then you multiply each row by that value. So it's a constant times a vector, constant times a vector. That's row operation, and then you add those up. A lot of people think, well, it's this times this, and this times this, and this times this, and that's how you go through matrix multiplication. Well, you can do it by taking that whole row, turning it sideways, and let that be a constant multiplier of each row. And that's how you need to think about it. This chip has vector multiplication on it. It does 2 multiplies and adds in 1 cycle. And we expect to see even more. Then they just move down 2 and do the next 2 pairs and so forth. But so instead of 4 cycles that it would normally take you to do that vector multiply, for each pair of 2s, it now is down to a single cycle. So understanding that when you're building an x prime x, it's vector multiplication. You're taking x1 times the first row, you're taking the x2 from the second row, and that's what you multiply that row by. And so these things don't have to be anywhere near each other. They can be scattered all over the place. And then when you invert that matrix to get a solution, again, you're using row operations. It doesn't matter. The rows don't have to be together. They can be scattered anywhere. You just have to have a little vector that tells you where they are. You've got to have a little housekeeping to know where they are. So it's pretty simple.
So you poked a little bit about the Internet of Things. Are you already starting to see in some of your conversations where some of those sensors and some of those feeds you think are going to change how we act, what we do?
Let me get around to it a little slower than that. We are working with a lot of sensor data right now. I've done some work right here with the Freedom Center on Centennial Campus, working with Duke Energy. They've got 140, no, it's 100, they have 104 synchro phasers. Now, these are not Star Trek phasers. These are these measure phaser measurements in the electricity that's coming through. But they're measuring 28 different measurements each time they do the measurements. They're doing 30 measurements a second. And we're getting that data, and Duke wants to know, tell us when something is going bad wrong so we can try to correct it. So, there we're dealing with incredibly fast data. So, big data can also be fast data, stuff that's really moving at you really, really fast. You've got to absorb it, do your computations on it, and end up with the results in milliseconds or even less. So that's one form of sensor. Cars all have all sort of sensors on them. 15 or 20 computers on every single car and chips. That's why you don't go poking around under the hood. You're going to blow a chip somewhere. So anyway, very soon now, all cars are going to be broadcasting information about all their measurements, all their meter, all their readings. So, and we're working right now with a trucking company that has 45,000 trucks that are going to send us 30 measurements every 5 minutes on each engine, speed, location, any number of things that they want us to be able to then analyze, help predict failures. That's one of the key uses of sensors, is to be able to predict failures, so that we can say that, and on the up in the Black Sea, where we do a lot, no, this is the North Sea, where we do a lot of oil exploration up there. There are pumps. There are like 200 pumps on every platform, and if any one of those pumps goes out, it's usually critical. So we are able to forecast when each one of those pumps is likely to fail, based on past history and using some of our analytical tools. So if a maintenance is scheduled and we're predicting the pump is going to fail within the next 2 months, they'll go ahead and replace it. Whether it works or not, they're going to replace it because we're predicting it's going to fail. Because if it fails when they're not expecting it, it's $10 million a day to shut that well down. So it's very important to these companies to keep these things up and running. Now, the Internet of Things, the idea is everything you own has an IP address, so that your refrigerator has an IP address, and your toaster has an IP address. And so your refrigerator and toaster can talk to each other all day. So, now this feeds into smart meters. Smart meters were this big thing that happened, it's been 4 or 5 years ago. A number of power companies said, oh my gosh, we can read meters every 15 minutes and get information about usage of electricity. So there's a number of power companies that have added smart meters to the houses. So they are broadcasting out every 15 minutes about energy use during that last 15 minutes. Well, there's a huge amount of data keeps piling up, and they don't know what to do with it. About the best thing that we've been able to figure out so far what to do with it is use it to forecast energy demand over the next few days or next few hours, so that if we see that there's going to be a huge demand occurring, and that demand is more than the supply that you've got, and you're going to have to go out and buy it on the open market, it can be very expensive. Yeah. Instead of 6 or 7 cents a kilowatt hour, sometimes they have to pay $2 or $3 a kilowatt hour to buy up excess power that is needed. So there's huge trading rooms that's all they do for energy companies is to make sure that they've got the energy needed, or they sell excess capacity that they have. But that's about the only thing it was good for, all these smart meter readings. But you see where they really come into play is when you have the smart meters and you have the Internet of Things on every device. So if all of a sudden you've got an energy demand peak that's coming up, the power company might just call up your dryer and say, hey, shut off for a little while, I'll tell you when you can come back on. Or he might just tell your refrigerator, go into a defrost cycle right now. So anything, or to cut your dishwasher off. I'm sure there will either be laws that permit this, or we're going to have to agree to it because we're going to get a better electric rate. But that's the long-term goal of the Internet of Things. I mean, already you've got thermostats that you can control through your phone, or you've got door locks or alarm systems that you can control through your phone. But eventually the idea is that everything is controllable. And I think it'll be a damn mess.
So we do want to open it up.
How do you turn that light off again? We used to have these switches on the walls, but now it's got to go through the Internet to talk to it.
So we do want to open it up for a few questions. And we got some hands. Do we have do we want to get a mic to them, or are we just letting them yell it out, Ken? Yell it out.
Well, I bought an airline one time. That didn't turn out to. It's called Midway Airlines. Went bankrupt a few years back. We bought a few companies that we didn't handle right when we bought them. We tried to integrate them right away. Now, if we ever do buy, and we do acquisitions every couple of years, we have learned to just leave them alone for a while, maybe pump them up with a little funding, a little device, but not to integrate them too rapidly. So, yeah, but the airline was the biggest.
Yeah. You got another question? Yeah.
I work for an engineering consulting firm. Been doing that for 30 years. We hire a lot of people from NC State, young engineers. With them comes new license for Java, Visual Basic, C++, Fortran 90, even MATLAB, but never SAS. I asked them why. They say, well, when I was a freshman, I was handed all these licenses and I don't have to mess with them. I just use them when I'm a student. And so they come already marketed. And SAS seems to be missing something.
Well, as a matter of fact, we've recognized that as an issue. Right now, any student anywhere in the world can download a copy of SAS free of charge for their machines. Since May, we've had 125,000 downloads. We have 20,000 students that are using our SAS on demand at our headquarters in Cary. So we are doing an awful lot of work to put SAS in the hands of our undergraduates and graduate students. We've also now have 30 universities that we've helped start a Master of Advanced Analytics degree. Our first one was here at NC State with Michael Rappa's group, and or he's moved over there, didn't he? Okay, Michael. He's graduating about 80 students a year and getting 800 applications for those 80 slots. Every one of his student graduates are getting 2 or 3 offers in very high salary range. So we recognize the problem, but it could be that some of the engineering departments think that this is a stat thing and they don't want to mess with it. But quite frankly, about 80% of any data analytical job is just getting the data ready, or extracting the data from different sources and merging it, or joining it together, whatever word you want to use. And that's what is one of the great strengths of SAS, is the ability to pull data together. So.
Another question over here.
You spoke about these companies like the one in the North Sea that would shut off its pumps just based on your recommendation. And I was wondering if you think it's possible to identify some of those key moments in SAS history where you were able to really build on that credibility.
Well, we've done, again, just about every new drug in the world goes through SAS analysis to be analyzed. We've helped save black rhinos in Africa. SAS has been used for a number of humanitarian relief things. We're working with the UN on disaster relief as rapidly as possible after tornadoes, and there we're using our visual analytics product to be able to spot where the need is. We're doing a lot of social media work there to be able to see what people are saying, what kind of tweets are coming out of this area about the conditions there. There are so many uses of SAS that people, they use it, and we don't necessarily even find out about it for some number of years.
I have a question on this side. Over here. One way in the back.
Do you still do any programming yourself, or have you transitioned into full management? Management is a bad thing.
You will find me programming occasionally, yes. I was just doing some work for our university edition to show people how to do simulations of coin tosses or simulations of dice rolls, to be able to create a data set of all possible permutations of a number, or to do any number of combinations, calculations, and those are tough little problems. Yeah, that's the latest thing I've done.
He's actually being a bit humble, right? As I was running R&D, it was not a surprise to come in on a Monday morning and Jim having an email to me saying, "I solved this over the weekend." Right? So more than once or twice that happened. Yes.
What were some of the challenges that the company faced in the earlier stages, and how were you able to overcome them and grow SAS to the company that the size that it is today?
I think one of the first problems we ran into is we sent our first secretary down to the A&P store to buy some coffee, and we gave her a check for $20, and they wouldn't give her any change. So to rectify that, she picked up a bag of M&Ms, and that brought it up to near $20. So they lasted about a week, and then John Saul said, "Where are the M&Ms?" So we had to go back and buy more, and we buy 2 tons a year now. So we are known for M&Ms. So anytime you come out to SAS, you're going to see M&Ms just about every break area.
So Jim, before we call it quits for the evening, you're very passionate about education. What would you say, 2 things, I think. What would you say about education in general, where you'd like for these people to be engaged? And second, to the students, when they're thinking about their education and what's important to the types of people that we're looking for, how would you coach them?
Well, right now we're looking at the country as a whole. I say we need about 10% more college graduates in the STEM areas. We are falling behind in innovation and creativity in this country because we are not producing enough STEM skilled students. It's not that they don't apply, and I was talking with Louis Vega on a panel. That was yesterday. I guess it was just yesterday. I was on a panel with him. We were talking about the fact that you get plenty of people into the engineering schools, but after a year they discover, these are tough courses, and they tend to switch curriculums and to switch majors. We have got to do a better job in K-12 of preparing students to be more rigorous, to study harder. We've got to raise the bar on education in the whole country, and especially here in North Carolina. We've had political changes under George Bush to have this No Child Left Behind thing, where everybody had to be smarter than average. And so everybody kept moving the bar down and down and down, so everybody could be past that bar, and it was left up to the states to set those bars themselves. And we really need to make that correction to how we're teaching students. We need better teachers. Our colleges of education need to prepare our teachers better. They're still preparing them the same way they did it 50 years ago. There's hardly any use of technology in the training of teachers, no use of data. There are just huge needs in education if this country is going to stay ahead.
So I think that's really important for everybody to be on board with that message. But to the students specifically in computer science and the things that you're looking for in talent when you're trying to find young people who really can engage, what would you tell them?
Well, we want people that are passionate about programming, that enjoy it, that are team players. One of the problems I think at university, you spend a lot of your time working on stuff on your own, but when you come to work for SAS, you've got to work in a team. You've got to be able to follow the procedures and processes that are in place, and most of them are in place for a reason, because we've made these mistakes before and don't want to make them again. So it's a totally different environment, but it's a great environment. I think all of you would enjoy it.
So I see Mladen standing over there with the hook, so I think we're about to get cut off for the evening.
Right.
So how about a round of applause for Jim here?